Okay, let's see. Okay, let me mute this. Okay, so now I think I'm in business. All right, so as I was saying, we'll be looking at the common way of naming compounds and the systematic way, which is actually the way that is used nowadays because it gives you more information. All right. So this basically this is mentioning that there are two ways of naming chemical compounds or identify them. You have the common names and the systematic names. Now the common names are very arbitrary, and as a result, they're not used that much when it comes to chemistry and in chemical literature. All right. They're not based on the composition of the compound. That's one important thing you need to realize. So in other words, if you're using a common name for the compound, you cannot tell exactly what the different, get this out of the way. You can't tell what the different elements are present in the compound, all right? Instead, they're based on some outstanding chemical or physical properties. Now in chemistry, because of the drawback we mentioned here in terms of not knowing the composition of the compound based on the arbitrary names, we prefer to use systematic names, all right? And the systematic names is useful because by looking at the name or knowing the rules for naming compounds based on, based on the system, which we're going to get into, we can tell what the chemical composition of the compound is, right? And the system that we use was devised by an organization known as the International Union of Pure and Applied Chemistry. So this is an organization, and in fact, there's a division within this organization. I think they meet every 2 years, if I'm not mistaken, in order to come up with rules for naming compounds. And the reason why they have to meet every 2 years is because every day a new compound is made, and very often the new compound, because of its structure or composition, provides a challenge in terms of naming based on the current rules. So therefore, the rules would have to be modified in order to accommodate any new compounds that have been synthesized. So that's why these guys have to meet every 2 years. All right. So just to give you some examples of different compounds, let me move this out of the way here. So we have some common compounds here. The common names on this side, the actual systematic names on this side, and we have the formula for the compounds in the middle right here. So for example, for this compound C2H2, the common name is acetylene, but the chemical name is ethine. Now, you would not know at this stage why this is a better alternative compared to this, because you'd have to be introduced to organic chemistry in order for you to appreciate that. However, if you look at the second example right here, CaO, right? That's a formula. The common name is lime, but the chemical name is calcium oxide. And even without knowing the rules for naming these compounds, you can tell that there's a relationship between the formula and the name, all right? Because based on the formula, you know that there are two elements, calcium and oxygen, and the name says calcium oxide. So one can obviously see the correlation between the chemical name and the formula, which is not the case if you look at the common name and the formula. Just by looking at lime, you cannot tell what the composition is. And the third example is similar to the second one. Again, based on the formula, you can see the correlation between it and the chemical name, which is calcium hydroxide. The formula is CaOH2. But again, if you look at the common name, that doesn't help you in terms of determining what the formula is. And we have other examples as well. So this basically, these examples, simple examples, just show you the difference between the common names and the chemical name. And as I said before, we're going to learn how to use the rules that we'll be covering to determine the formula if given the name and vice versa. But before we do that, we have to be introduced to certain terms and ideas, concepts. We talked about elements already. We know that elements are basically the simplest known substances that cannot be broken down into anything simpler by chemical means, right? And of course, elements have their own specific formulas each, and these are just some examples right here. Sodium, potassium, and so on. So those are the formulas for these elements, all right? Now, there are certain elements that exist in nature as diatomic molecules, and it is your responsibility to simply know them, right? So for example, if you're given a question, and let's say the question is talking about the reaction of fluorine, then you should immediately understand that what they're talking about is fluorine existing as a diatomic molecule, and the formula for that would be F2, all right? So these 7 elements, you need to know them and remember that they do exist in nature as diatomic molecules, all right? Then we have some other elements which are said to be polyatomic, and they only told them actually here. They exist in nature as polyatomic molecules. Sulfur exists as S8 and phosphorus exists as P4, all right? So again, you need to know these two, right? And you need to keep in mind that this is how they exist in nature. So if a question is talking about a reaction with, let's say, phosphorus, then you should know that you're referring to P4, all right, and not just P, okay? Also, we need to talk about ions, all right? What are ions? Ions are charged particles which can be produced by adding or removing one or more electrons from a neutral atom. Now, if you may recall, a neutral atom will have the same number of electrons and protons, right? So if you take, for example, sodium, and the atomic number gives you the number of protons, then which is equal to 11, then the number of electrons will be equal to 11 as well, because for a neutral atom, the number of protons and electrons must be equal. So how do ions, well, as we said before, ions are produced by adding or removing one or more electrons from a neutral atom. So what we're going to look at here is the example of the potassium atom, all right? The potassium atom has 19 protons in the nucleus and 19 electrons surrounding it. And what will happen is that potassium tends to, let me move this up here, potassium tends to lose one electron to form what is known as the potassium ion. And in this case, the number of protons does not change, but of course the number of electrons will change from 19 over here to 18 here. So the result would be a structure where you have one more proton more than electrons, right? And therefore what will happen as a result is that the resulting structure will have a net positive charge. And we call that the potassium ion. And you'll notice that the symbol for the potassium ion has a plus charge right here, all right? So that plus charge basically indicates that the atom or the ion is one electron short of the number of protons that is present. So the name we call this type of ion, which is positively charged, we call it a cation, all right? So cations are basically ions that are positively charged, all right? Okay, then we get to other examples. So potassium, of course, is not the only example of an atom that will lose electrons. You can have sodium losing one electron to form the sodium ion. We have calcium losing 2 electrons to form the calcium ion. And please note, as a result of the loss of 2 electrons here, the calcium ion ends up with a +2 charge, all right? So the pattern that you see emerging is that whatever the number of electrons being lost, the number of plus charges will be the same, all right? If you have 1 electron lost, then there will be a +1 charge remaining on the ion. If there are 2 electrons lost, then there will be a +2 charge remaining on the ion. And then when we get to this third example of aluminum, which loses 3 electrons for every atom, the charge left on the aluminum ion will be +3, all right? Now, later on, we're going to learn how to predict the number of electrons that will be lost. And what you're going to find is that the number of electrons lost by each atom is a function of the position of the element in the periodic table. So that's for later on. We're going to discuss that later on. But for now, just accept that this is a situation for each of these atoms. Okay, so how do we name cations? Well, according to IUPAC, it's very easy. The cations are named the same as the apparent atoms, all right? So whatever the name of the atom that is forming the ion is, the name of the cations will be the same, all right? So for example, in the case of the sodium atom, which loses an electron to form the Na+ symbol right here, the name of that cation would be the sodium ion, all right? In the case of the calcium atom, it forms a calcium ion. In the name of the lithium atom, it forms the lithium ion, all right? In the case of the magnesium atom, it forms the magnesium ion, okay? So basically, whatever the name of the atom that is forming the positive ion, the name of the ion will be the same thing. So we have strontium here, it forms a strontium ion, all right? So that's basically how we name these cations, all right? Now, on the other hand, where we have atoms gaining one or more electrons, then it will form what is called an anion, which would be a negative ion, all right? So a negative ion is the same thing as an anion. So for example, if we look at the chlorine atom, which has 17 protons in the nucleus and 17 electrons surrounding the nucleus, what will happen in the case of chlorine is that the chlorine atom, which is neutral, is more likely, very likely, to gain an electron to form this structure where you now have a total of 18 electrons, the number of protons remain the same, and therefore, as a result, because of the fact that you have one more electron than proton, the resulting structure will have an overall negative charge. So therefore, this is a symbol for this particular ion, Cl with a minus charge right here. And the name of this ion is called the chloride ion, all right? So we're going to look at how we name ions that are formed as a result of adding electrons to an atom. As I said before, the negative ion is called an anion. So this will be the anion formed from the chlorine atom. So as promised, we're going to talk about how do we name anions. Well, things are a bit different when it comes to naming anions, because what you'd have to do in order to name a particular anion is that you take the stem of the parent name element and then you add an IDE ending to it. So all the names of these anions that are formed from atoms, names are ending with IDE or IDE, all right? So for example, the fluorine atom, when it gains an electron, forms what is known as the fluoride ion, right? We replace the INE in the case of fluorine with IDE to name the anion, all right? So the stem, of course, will be the fluor, and the ending will be the IDE. Similar thing will happen in the case of chlorine, right? When chlorine gains an electron, it forms a chloride ion, all right? So again, we replace the INE here with the IDE ending to get the name of the corresponding anion. Same thing with bromine. The INE ending is replaced with IDE, so the name of the anion formed from bromine is called the bromide ion. In the case of nitrogen, what happens in this case is that the OGEN of this part of the name of that element is replaced with IDE. So therefore, the name of the anion is the nitride ion, all right? And please note that the charge here in the case of nitrogen is -3, all right? In the case of the nitride ion is -3, all right? And again, the charge is based on the relative positions of the elements in the periodic table. As promised, I will get to that later on. Here's another example, phosphorus. When it gains 3 electrons, it forms what is known as the phosphide ion, again, the IDE ending, all right? In the case of oxygen, it gains 2 electrons to form the oxide ion, all right? And basically, that's how we have ions deriving their names from their respective atoms. We replace the ending of the names of these elements with IDE to get the names of the corresponding anions. Okay, so we talked about the fact that cations are formed as a result of electrons being lost by an atom, and anions are formed as a result of electrons being gained by an atom. So if we look at the way ions are formed to form a compound, basically what you have is that ions are always formed by adding or removing electrons from an atom. Most often, what happens is that these ions that are formed when metals combine with nonmetals. And as stated here, the charge on an anion or an ion can to some extent be predicted from its position in the periodic table, all right? And we're going to see some examples of this in this slide right here. So if you look at this slide, you'll notice certain patterns emerging for certain elements in certain groups. What you'll find is that elements in the A group or A part of the periodic table, we're talking about groups 1A, 2A, 3A, 4A, 5A, 6A, and 7A, you'll find that you can make certain predictions about the type of charges that these ions will have. So what you'll find, for example, is that elements in group 1A tend to have a +1 charge in their ions, all right? And that's because these elements tend to lose only one electron from their atoms to form the ion. In the case of elements in group 2A, they tend to lose 2 electrons, right? And therefore, they tend to have a +2 charge. And then over here, in the case of elements in, well, let me say here, for elements in 3A, they tend to lose 3 electrons for the most part. Now, there's some exceptions. Boron, for example, tends not to do so because boron is not a metal. We're going to get into that discussion later on. But aluminum is one such element which will lose 3 electrons to form the Al3 plus ion. Now, that's as far as metals are concerned. They tend to lose electrons. In the case of nonmetals, they tend to gain electrons. So what you'll see, for example, elements in group 7A, they tend to gain 1 electron to form a negatively charged ion with only 1 negative charge. In the case of the elements in group 6A, they tend to gain 2 electrons. And in the case of elements in group A, they tend to gain 5 electrons. And these numbers, the number of electrons gained, is related to the electronic structure, which we're going to get into later on, all right? Now, what is very difficult to predict are the charges formed by elements in this region, right? This is known as the transition region. And what you'll find is that unlike in the case of groups 1A through 7A, it's very difficult to predict the type of charges that will be formed by the ions in this region, all right? So I wouldn't expect you to be able to make such predictions. And that's the reason why I've provided the charts in Canvas for you to refer to, all right? But one thing I want to point out here, well, okay, let me scratch that. I was going to say something, but that will be discussed later on. Let's talk about writing formulas from the names of ionic compounds. So what we're going to learn here is how do we determine the formula based on the names of your ionic compound. Now, the first thing you need to be aware of when doing this is that the chemical compound, and it doesn't matter if it's ionic or covalent, must have a net charge of 0. Now, in the case of ionic compounds, what that means is that the total number of plus charges must be equal to the total number of negative charges, so that all the charges, when added up, will end up to a net of 0 in terms of the charges, all right? So that's something that you need to keep in mind when doing problems like this. So in this particular example, you're given the formulas for these 3 compounds, all right? So the way you do this, and let me, how am I going to do this now? Because I don't think I'm able, oh, wait a minute. Okay, all right, so in the case of the first example, you're given calcium, okay, it's not writing. Oh shoot, okay. That means, and okay, what am I gonna do? What am I gonna do? What am I gonna do? Okay, this is not, for some reason, when I'm sharing my screen, I'm not able to write on this. And unfortunately, I do not have, okay, let me try something here. Let me try Word. Let me see, where's the writing? Okay, what's happening here? Okay. Okay, this is not working out for me. Let me get out of this here. Okay, I don't know why this is not cooperating. Let me try. Let me try this again. Oh, okay, I don't know why. Let's see if this will work now. Let me try this now. Okay, it's working. Okay, so in the case of calcium chloride, the first thing I would do is that I would consult the chart with the list of ions, all right? And when I do that, I will see that calcium has a +2 charge. So I'm going to put Ca2 plus here, all right? And then I'll look up the chloride ions, and I see that chloride has a -1 charge. So the formula for the chloride will be Cl minus, okay? So as I said before, the total number of plus charges must be equal to the total number of negative charges. So as we have it right now, that's not the case. We have a 2 plus charge here, and we have a -1 charge here for the chloride. So what I would do is I would put a 2 here. Now, by doing that, that would double the charges here for the chloride from -1 to -2, which will exactly cancel out the 2 plus charges on the calcium ion here. So when I put this together, the final answer is going to be CaCl2. All right, so this 2 that we have here, that we multiply the chloride by, will become the subscript in the final formula. All right, so this would be the formula for calcium chloride. In the case of barium phosphide, it's the same approach. You go to the table, you look up the formula for the barium ion, which would be Ba2 plus, and then you look up the formula for the phosphide ion, which would be P3 minus, and then I'll ask myself, how do I get the charges equal? Because as it is right now, you have a +2 charge here and you have a -3 charge here. Whoops. Sorry about that. I don't know where that happened. So what I would do in this case is that I would multiply this here by 3 and this by 2. Because when I multiply 3 times +2, I get a total charge here of +6. And when I multiply 2 times -3, I get a total charge here of -6. So the charges are canceling out. So when I put this together, the final answer becomes Ba3P2. So this would be the formula for barium phosphide. All right. Any questions so far? Any questions? No? Okay. So if you understand that, those two, then how would you determine the formula for magnesium oxide? What would be the first thing you would do? Anybody? And by the way, this one should be the easiest of these problems right here. So
Find both of the charges of each element.
okay, so for magnesium, what's the charge?
+1.
You sure?
Oh wait, no, I lied. Sorry, hold on. Let me look at my.
Yes, please consult the tables that I provided.
It's 2 plus.
Right, 2 plus. And what's the charge on the oxide ion? Oops.
2 minus.
2 minus. So what do you think is going to happen in this case?
They're just going to cancel out.
Exactly. So the final answer is going to be what?
MgO.
MgO, correct. All right, so that's basically how you would determine the formulas based on their names. And if you understand that, then you should also be able to do the reverse. If you're given the formulas, then you should be able to determine what the names of the compounds are. All right? Okay, so that's basically how that is done. Okay, now what we're going to talk about is specifically how do we name binary ionic compounds. So when we're talking about binary ionic compounds, we're talking about ionic compounds which are made up of only 2 elements. One would be a metal and the other one would be a non-metal. All right? So as stated, binary compounds contain only 2 different elements, and it happens when you have a metal combined with a non-metal. All right, so what you're going to see is that there are several types of binary compounds. So the first type we're going to look at is one where you have a metal ion that forms only one type of cation. All right, so how do we name them? Well, the chemical name is composed of the name of the metal first, followed by the name of the non-metal that has been modified to an identifying stem plus the suffix IDE. So if you remember, we talked about the IDE ending that comes into play here again. All right. So in this case, one thing you need to recognize is that the number of atoms of each element is not expressed in the name. So we're not concerned with naming ionic compounds or binary ionic compounds. We're not concerned with indicating the number of atoms or ions present or represented in the formula. All right, that will become important later on when we're talking about molecular compounds. Okay, so basically this is a summary of how we name binary ionic compounds, right? We start out with the name of the metal, then the stem of the name of the nonmetal, and then we have the IDE ending attached to the stem of the name of the nonmetal. All right, that's basically how we name these types of compounds. So we're looking at, for example, this compound right here, CAF2, right? So question is, how do we name this compound? It says in step 1, from the formula, we know it's a 2-element compound, so therefore we know it's a binary compound, and therefore we follow the rules concerning binary compounds. Then what we do next is that we basically identify the cation, which of course will be the calcium ion. All right, so the first part of the name will be calcium, all right? And the other part of the name would be due to the fluorine, but of course we cannot use the full name of the fluorine. We have to use the first part of the name, the fluor, and then we end it with IDE. So the negative part, or the second part of the name of the compound, would be fluoride. And then all you have to do is put them together, and therefore the name of this compound is calcium fluoride. So it's pretty simple and straightforward when it comes to naming the compound based on the formula. And an added advantage that you guys have is that you can consult the table to look up the name, right? The tables with the list of common ions. You can consult that table to look up the name of the ion that you want to figure out the name of, all right? So that's basically how we do calcium fluoride, all right? So let's look at some other examples. So in the case of NaCl, the name of this compound will be sodium chloride. The first part would come from the name of the metallic part of the compound, and then the second part comes from the stem of the nonmetal name, followed by IDE, all right? So therefore, the name of this compound is sodium chloride. Here's another example, MgCl2. The first part would be the name of the metal. The second part would be the nonmetal stem, followed by the IDE ending. And please note, even though we have a 2 here, right? Let me get out of this here. Even though we have a 2 here, we do not indicate the number of chloride ions in the name itself, all right? So that's basically the name of this compound. Here's another example, K2O, right? The first part would be potassium, which would be the name of the metal. And then the second part would be the stem of the oxygen name, followed by IDE. So the name of this compound is potassium oxide, all right? Here's another example, Na3P. First part is the metal name, which is sodium. And then the second part starts off with the stem of the phosphorus name, followed by IDE. So therefore, the name of this compound is sodium phosphide. I think, oh, okay, so those are the examples. So this table basically summarizes how you derive the anion names from the element name, all right? And in each case, you start off with the stem of the element name, in the case of the nonmetals, and they all end with IDE, right? So bromine becomes bromide, chlorine becomes chloride, fluorine becomes fluoride, and so on and so forth. So this is something that you need to basically remember when it comes to naming binary ionic compounds, especially with respect to the name of the nonmetallic part of such compounds, all right? So some examples are given here of binary ionic compounds, how they're named. So I'm just going to point to a couple of examples. For example, this compound here is known as calcium carbide. This one is known as magnesium bromide. I think we saw that before. This is called sodium hydride. And in all cases, you start off with the name of the metal first, the full name of the metal first, then the stem of the name of the nonmetal, and then we end that part of it with IDE, all right? So that's basically how we name these compounds. All right, now there's a second type of binary ionic compound that we need to be concerned with, and that are compounds which contains a metal that can form 2 or more types of cations, all right? So there's some particular elements, metallic elements, that can form ions of different charges. So in order for us to know how to name these compounds, I'm going to introduce to you the stock system of naming them, and then the other system, which is the classical system. So in the case of the stock system, what we do is that for elements such as chromium or iron or copper that can display more than one charge, as you can see here, what we do is that, so iron is one example, Fe2 plus, that's one form of ion, and then there's another form which has the plus 3 charge, all right? So we have to be able to distinguish between these two by name, all right? So how do we distinguish between them? Well, before we do that, let's look at the type of compounds formed by these ions when they combine with sulfur. So if you're using Fe2 plus to combine with sulfide, then you're going to get this formula here. But if you use Fe3 plus, you're going to get this formula, all right? So these are two different compounds, even though they're made up of the same elements, but they're different simply because they have a different composition in each case, all right? Okay, so as I said before, the stock system is what we're going to use to make a distinction between these types of ions. And IUPAC came up with this system. And basically what the stock system involves is that in order to indicate the charge of the cation in the name, we use a Roman numeral placed within parentheses immediately following the name of the metal, all right? So the Roman numerals, of course, I'm quite sure you're all familiar with, right? I for 1, 2 I's for 2, and so on. IV for 4, and V for 5. So those are the Roman numerals that you use for the respective charges, all right? So these are the symbols that we're going to use right beside the name of the particular metal ion in order to indicate the corresponding charge. And let me see what's down here. Oh, and by the way, because we're talking about binary ionic compounds, the non-metal name will still end with IDE, just like we saw in the previous example, all right? So here are some examples of different ions, ions of the same element that carries different charges. So copper can be expressed as an ion as either the one carrying the +1 charge or the other one carrying the +2 charge. The one that carries the +1 charge is known as copper 1. The one that carries the +2 charge is known as copper 2. There are also two types of iron ions, such as the Fe2 plus and Fe3 plus. Those are the symbols, and these are their names. This one is called iron 2, and this one is called iron 3. And then we have lead, which exists as 2 plus or 4 plus in terms of their ionic charge. So the 2 plus form of lead ion is called lead 2, and the one that carries a 4 plus charge is called lead 4. Now, this one is a bit tricky, all right? Mercury. Mercury exists as this form and this form, but you'll notice that both of them carry the +2 charge. But this one has 2 atoms of mercury. So basically, these 2 atoms here collectively carry a +2 charge, which basically means that there's a charge for each atom. So therefore, this is called mercury 1, right? While this one is only 1 atom that makes up this ion. So therefore, this is called mercury 2, all right? And then finally, we have tin, which can exist as the +2 ion or the +4 ion, and these are their names correspondingly, all right? So that's basically how we indicate the names of the ions based on the charges that they carry. Okay, let me move on. Okay, so let's look at some examples here. So if we look at these 2 compounds here, all right, FeCl2, FeCl3, right? Obviously, same elements that make up these 2 compounds, but their compositions are different, all right? So the question now becomes, how do we name these compounds? Well, in order for us to name these compounds, we need to determine the charge carried by the iron ion in each case. So because the chloride ion carries a -1 charge, in this case, because we have 2 chloride ions, that means that the iron here must carry a +2 charge. In this case, because we have 3 chloride ions here, that means that this iron ion must carry a +3 charge, all right? So when it comes to naming these compounds or these ions, the name of the iron here, the name of the iron ion here would be iron 2, and the name of the ion here would be iron 3. The chloride name would still be applied to each of these right here. So therefore, when we put the names together for each compound, the name of the first one will be iron 2 chloride, and the name of the second one will be iron 3 chloride. All right, so that's basically how you would determine the name based on the formulas for these compounds. All right. Okay, any questions about this example? Any questions? Any questions? Okay, so let's move along to this example right here. So in this case, we have two compounds which contain tin and bromine. The formula for this one is SnBr2, and the formula for this one is SnBr4, all right? So the first thing we need to do is determine the ion charges, right? So my question to you is, what would be the charges for the ions in the case of the first one? Anybody? And by the way, let me look at the chat here. Okay, so Alexandra is asking, will we be given a chart of the ion charges, or must we memorize this? Yes, you will be given a chart with the ion charge. It's the same chart that is posted in Canvas, all right? So I hope that answers your question, Alexandra. Okay, Alyssa. Okay, so +2 applies to which ion? Okay, so in the case of tin, and I'm assuming that you're referring to the tin here, right? Okay, so that's +2. Now, why do you know, or how did you know that it was +2? And anybody can answer. How do you know it's +2? Anybody? I mean, she's right. She's right that this is +2. The charge for the tin is +2, right? And we know that that is +2 because we have 2 bromide ions here, right? So the total net charge carried by the 2 bromides will be -1. I'm sorry, -2. So therefore, this must be +2 in order for the compound to be neutral. Okay. So what about the tin in the case of the second compound? What is the charge carried by the tin here? Let me see if anybody's answering that question in the chat. Okay, so, somebody, Evan Brown says +4, that's correct. And Taryn actually jumped the gun to answer the question. So let me show the charges. So +4 will be the charge for the tin. The bromide will still be -1. So the ion names would be, in the case of this one, tin 2, and this is bromide. And in the case of this one, it will be tin 4, bromide. So therefore, when you put the names together, the name of the first one will be tin 2 bromide, and the name of the second one will be tin 4 bromide. Okay, so that's basically how we name these types of compounds, right? So remember, when we have situation where we have an element, a metallic element that can display ions of more than one charge, you have to use Roman numerals to indicate the charge that is carried by that particular ion in a particular compound, all right? Now, if you're dealing with an ion that carries only one charge, then according to IUPAC, no Roman numerals should be used, all right? So that's something you need to remember. So for example, hold on. So for example, let me see if I can write something here just to show an example. So for example, in the case of sodium chloride, the formula for sodium chloride is NaCl without any Roman numerals. So therefore, according to IUPAC, if you did this, put a 1 here to indicate the charge. For the sodium, that is not right, all right? It's simply Na, I'm sorry for how this looks, folks. NaCl, Cl, right? So that would be the formula for sodium chloride. I just thought I should show you that so that you understand how to use or when to use the Roman numerals. Okay, so let's talk about the other type of system, which is the classical system, which is an older system. And it's not as easy to use as in the case of the stock system, but we're going to talk about it anyway, because sometimes you see the system in certain chemical literature. And basically the classical system, what happens is that the name of the metal is modified with the suffixes OUS and IC, or us and IC, all right? So basically, the thing about using the system is that you cannot tell the actual charges based on the names directly. All you can tell is that the metal ion that ends with the OUS ending has a lower charge, and the one with the higher charge will have the IC ending. In any case, the non-metallic name ends with IDE, all right? So let's see some examples of this. So if you remember these two examples here, right, where the charges are for iron here is +2 and for iron here is +3. The name of the ions, according to the classical system, is that this one is called the ferrous ion and this one is called the ferric ion, all right? And therefore the name of this compound would be ferrous chloride, the first one, and the name of the second one would be ferric chloride, all right? So that's basically how the classical system works. So as I said before, you cannot tell exactly what the charge is based on the names. All you can tell is that the one that ends with OUS will have a lower charge compared to the one that ends with IC, all right? Here's another example. The first one is called stannous bromide, and the second one is called stannic bromide. Again, the OUS would have a lower charge compared to the IC when it comes to comparing these two. So the name of the first one will be stannous bromide, the name of the second one will be stannic bromide, all right? Okay, so basically this is a summary of the classical system in terms of the ion names. And again, you see the same thing as we saw in the examples. The OUS ending, the ion with the OUS ending would have a lower charge compared to the ion with the IC ending. Again, you cannot tell exactly what the charges are based on simply looking at the names according to the classical system, all right? Okay, so what time is it? Let's see how much time we have left. Okay, so let's talk about compounds containing polyatomic ions, all right? How do we name these compounds? So let's talk about what we mean by this term polyatomic ion. And as stated right here, a polyatomic ion is an ion that contains 2 or more elements. All right, so an example of a polyatomic ion would be this one right here. So in this particular case, you have nitrogen combined with 3 oxygen atoms, and that unit carries a negative charge, right? So that's what we mean by a polyatomic ion. And there are several examples of polyatomic ions we can point to. Now, basically, what you'll find is that compounds containing polyatomic ions are made up of 3 or more elements, all right? They usually consist of 1 or more cations combined with a negatively charged polyatomic ion. So here's one example, right? This compound is known as sodium carbonate. And as you can see, you have the sodium here, which would be the cation, and then you have the carbonate ion here, which would be the polyatomic ion. So the sodium ion is monoatomic, but the carbonate ion is polyatomic, all right? So the sodium is the cation and the carbonate would be the polyatomic anion, all right? So when naming these compounds, just as we would do in the case of binary ionic compounds, we start off with the name of the positive ion first, followed by the name of the anion, all right? So the name of this compound, as I said before, is sodium carbonate, all right? Okay, so this is another example. Now, in this case, we have the potassium ion combining with this ion. This ion is called the permanganate ion, right? So this is what they look like together, but of course, they're made up of these different ions, right? So these are the ions that are actually present in the compound, but this is the way that we write the formula representing that compound, all right? Here's another example. In fact, we saw this example earlier, sodium carbonate. So in the case of sodium carbonate, it consists of two sodium ions, right? So we would actually write them separately like this. You have the 2 in front of the Na plus here, and the carbonate ion, which carries a -2. And you'll notice that the charges will cancel out because you have this 2 here. This 2 will double the plus charge here. So the total number of charges here will be +2, which cancels out the 2 minus 2, the 2 negative charges here to end up with an electrically neutral ionic compound. All right. Now, let's talk more about the name of these compounds. And there are certain patterns that will emerge. The first of which is mentioned right here. Anions ending in 8 always contain more oxygen than the anions ending with ITE. All right. So you cannot again tell the number of oxygen atoms present, but you can tell that the ATE naming or the anion ending with ATE will have 1 more oxygen compared to the anion ending with ITE. So, for example, if you compare these two, right, this is called the nitrite ion and this is called the nitrate ion. And you'll notice that the nitrate has 1 more oxygen compared to the nitrite ion, all right? Another example here is the comparison between the phosphite ion and the phosphate ion. Again, you'll notice that the phosphate ion has 1 more oxygen compared to the phosphite ion, all right? I think there's one more example here, comparing the sulfite and the sulfate ion. Again, you see that the sulfate has 1 more oxygen compared to the sulfite. So you can see that in each case, based on the name only, you cannot tell exactly what the number of oxygen atoms are, but you can tell that the one that ends with ATE will have 1 more oxygen compared to the anion that ends with ITE. All right, so that's basically what you can observe when you compare these types of ions with these names. All right, so I stated here the H and the I do not indicate the actual number of oxygen atoms. All right, now there are some other things that can be added to the names of anions which indicate, again, the fact that there are more oxygens present in one form compared to the other. So if you see the term per or the prefix per before the name of the particular ion, then that means that it has 1 more oxygen compared to the 8th form. All right. So for example, this is called the chlorate ion, ClO3 minus. Now, if you add 1 oxygen to this, it becomes the perchlorate ion. So the perchlorate ion will have 1 more oxygen compared to the chlorate ion. All right. Here's another example. Oh, well, a different issue. If you see the prefix hypo, basically what that indicates is that the anion which carries that name will have 1 less oxygen compared to the one that ends with simply ITE. So for example, this is called the hypochlorite ion, all right? And if you compare this to the chloride ion, you'll notice that the chloride has 1 more oxygen compared to the hypochlorite, all right? So again, you cannot tell exactly the number of oxygens that are present in these structures, but you can tell which has more oxygen than which, all right? The chloride, or anything that ends with ITE, will have 1 more oxygen compared to the name, the one that names start with hypo, stem of the name of the other element, followed by ITE, all right? So that's basically what that tells you. Okay, and then another thing I need to mention here is that there are 4 polyatomic ions that do not end with ATE or ITE. So these are a bit unique in their own regard. You have the hydroxide, you have the cyanide, you have the hydrogen sulfide, and you have the peroxide, all right? So they don't basically follow the rules when it comes to the ATE, ITE system, all right? So these are just some unique situations. In any case, you don't need to memorize all these rules for my class because, as I said before, you'll have access to the tables, especially doing your test. So all you have to do in order to figure out what the name is consult the table if you're given a formula and vice versa. Okay, let me see. Oh, these are also unique. Most of the polyatomic ions that exist are negatively charged ions or anions. But here we have 3 polyatomic ions which are positively charged. So these are a unique group, right? you have the hydronium, you have the ammonium, and you have the mercury one. All right, so these are the only ones, at least at this level, that you need to be concerned with as far as being polyatomic is concerned. All right. Okay, so just to give you some examples of different ions and their formulas and their charges, we have this list right here. These are the cations on the left, the anions on the right. So, well, actually, we have some anions here on the left as well. So, we have the ammonium, which is positively charged. We have the arsenate, which is one that carries a -3 charge. We have nitrite, we have nitrate, we have permanganate, and so on and so forth. So, as I said before, in your chart, the table that you're given in Canvas, that's a more comprehensive list that you'll have access to. And these are just some compounds that make up, that consist of actually polyatomic ions, such as potassium hydrogen sulfate, magnesium ammonium phosphate, potassium aluminum sulfate, and so on and so forth. So these are all examples of compounds that contain positive, polyatomic ions. And not only that, but they contain more than one type of positive ion. So for example, in the case of potassium hydrogen sulfate, you have two positive ions here, potassium and hydrogen, right? And then you have the sulfate, which is the anion, all right? So that's as far as that is concerned. Okay, let's see how we're doing on time. Okay, we have 50 minutes. Okay, let me start this topic and we'll just stop whenever the time runs out. So now we're going to look at how do we name binary molecular compounds. So binary again means two, but now we're talking about molecular compounds, not ionic compounds. So what we're talking about here are compounds that are formed between nonmetals. So binary molecular compounds are made up of two nonmetallic elements, right? So therefore they're not ionic, all right? So how do we name these compounds? Well, according to the rule of thumb established by IUPAC, in a compound formed between the two nonmetals, the element that is farthest down and to the left on the periodic table is the one that is usually written first. And when I say written first, I mean written first not only with respect to the formula, but also with respect to the name. So another way of stating this is that the more metallic element is written first. So basically what this is saying is that if you have two non-metallic elements coming together to form a binary molecular compound, in the name and in the formula, the first element is the one that is furthest to the left in the periodic table and furthest down in the periodic table, all right? So for example, let's say we have, let me see if I have an example here. Oh, I don't, okay. So let's say, for example, let me do a little scribbling down here. So let's say we have a compound formed between carbon and oxygen, right? If you look at the periodic table, you'll see that carbon is to the left of oxygen in the same row, right? So in the formula, if let's say it's one carbon atom for every two oxygen atoms, then the formula would be CO2, all right? So basically the carbon is indicated first and then the oxygen after, all right? Here's another example. Let's say we have a compound formed between sulfur and fluorine. Well, sulfur, if you look at the periodic table, sulfur is to the left of fluorine and down. So therefore, the sulfur would be first, followed by the fluorine. So let's say the formula is SF4, then this is basically the order. The sulfur first, then the fluorine. All right, so that's basically how we indicate the order of the elements when it comes to writing down the formulas, and as you're going to see shortly, when it comes to determining the name of the compound. Okay, so let's talk about the use of prefixes. So this is one big difference between naming ionic compounds and naming molecular compounds. In the case of naming ionic compounds, we do not use prefixes to indicate the number of atoms represented in the formula. However, when it comes to naming molecular compounds, then we have to use the appropriate Greek prefix that is placed before the name of each element. And the purpose of that is to indicate the number of atoms of the element that is present in the molecule. Now, key thing you need to remember is this. There are certain exceptions to the use of the prefixes. And these exceptions are listed down here, right? The first exception, let me go back to my pointer here. The first exception is that if there's only one atom of the first element in the formula, then we use no prefixes for that element, all right? So if you have two elements, the first one, which would be the one that is furthest to the left and down in the periodic table compared to the other one, if that first element has only one atom represented in the formula, then we do not use any prefixes for that element, all right? Now, if there's more than one, then you'd have to use the appropriate prefix, and we're going to show you what the prefixes are. The other exception is if you have a binary molecular compound containing hydrogen, then basically there are no prefixes that are used to indicate the number of hydrogen atoms. In fact, I would take it a step further and say that there's no prefixes that you use at all in that compound, all right? So those are the two exceptions to the use of prefixes. Otherwise, you have to use the prefixes to indicate the number of atoms of each element present. And we're going to see some examples of this. So let's see here. So these are the prefixes that you'll be using. Make sure they all appear, right? Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. And we're going to stop here for all purposes because you can go beyond 10, but for all purposes, we'll just stop here, all right? So these are the common prefixes that you'd have to use whenever you're naming binary molecular compounds. Of course, taking into account the exceptions that I talked about earlier. Okay, so as stated before, one of the exceptions is that we do not indicate any prefixes for the first element if there's only one atom of that element represented in that formula, all right? Okay, so let's look at some examples and you're going to see how this works, all right? So in this case here, we have N2O3, all right? So we have 2 atoms represented here for the nitrogen and 3 atoms here represented for the oxygen. So the prefix that we will use in front of the nitrogen would be di, and the prefix that we will use for the oxygen will be tri, all right? So another thing you need to remember is that for the first element, we use the full name, but for the second element, it ends with IDE. So the name of this compound here, let me just skip all this here. The name of this compound here is dinitrogen trioxide. Dinitrogen trioxide, all right? Di, because there are 2 nitrogen atoms, so that's where the dinitrogen comes from. And the tri comes from the fact that there are 3 oxygen atoms. But remember now, for the second element, its name must end with IDE. So therefore, that's why it's called trioxide. So the full name is dinitrogen trioxide, all right? Any questions about this example? Any questions? Any questions? Okay, the next example is this one. Now this one, you'll notice that there's only 1 atom of phosphorus, which is the first element here, right? Followed by 5 atoms of chlorine. So in this particular case, right? Remember now, we said that if there's only 1 atom for the first element, we do not use any prefixes. So we would not use mono for that one. But for the second element, we would use the prefix for 5, which is penta. So therefore, the name of this compound here is phosphorus pentachloride. Phosphorus pentachloride. There's no mono in front of the phosphorus pentachloride because there's only 1 atom. According to the rules, if there's only 1 atom for the first element, then we do not use the mono prefix, all right? But we do have to use the penta prefix for the second element. So it's monophosphorus pentachloride, all right? So that's how we name that. Okay, so let's see if you can name this compound based on what we have, based on the examples that we have looked at so far. So would anybody want to take a stab at this one? Let me check out the chat here. Okay, Alexandra, I'd have to talk to you about that later. Can't talk to you about that right now, all right? Okay, so who would like to take a stab at this one? What's the name of this compound here? Well,
Dichlorine heptaoxide.
You're absolutely right. Dichlorine heptaoxide. Again, in this case, we have 2 atoms of chlorine, so that's where the dichlorine comes from. And then we have 7 oxygen atoms, so therefore we call this heptaoxide. Now, let me just say that in some textbooks, they might leave out the A here, so the name would be heptoxide. And according to IUPAC, that is just as correct, right? So you can call this heptaoxide, or you can simply call it heptoxide, all right? Either works, all right? Okay, very good. So that's the name of that compound, dichlorine heptaoxide. Okay, let's look at some other examples. Okay, so who'd like to take a stab at this one? What do you think the name of this compound is?
It's dichlorine trioxide.
Exactly, dichlorine trioxide. Very good. Okay, let's see here. Of course, you understand where the dichlorine comes from and where the trioxide comes from. Okay, very good. Okay, another one. Who'd like to take a stab at this one? And by the way, this is not an I. I can understand if somebody thinks that this is actually an L, lowercase l, right here. So what's the name of this one? Well?
Carbon tetrachloride.
Carbon tetrachloride, very good. Carbon tetrachloride, all right? Okay, and what about this one? Let me move this down here, out of the way. What about this one? Let me see. Oh, okay, Alyssa is answering the carbon tetrachloride, okay. And Alyssa just answered this one. And Alyssa, you are correct. This one is called carbon monoxide. All right, okay, very good. What about this one? Well, this one is too easy. What's the name of this one? Anybody?
Carbon dioxide.
Carbon dioxide, yeah, exactly. Okay, what about this one? Now, in this case, this is actually a letter I, all right? So, what do you think the name of this one is?
Phosphorus triiodine. Iodide.
Iodide, exactly. Phosphorus triiodide. Very good. Okay. I think there might be one more. Hold on, let me see that. Okay, no more. All right, you know what? I'm going to stop here for today. But before I let you guys go, let me direct you to discard this. Some assignments I want you to do. So let me go to files and then assignments. And we're in chapter 5. So basically, all right, this is out of order, unfortunately. Well, actually, no. Okay, so you should be able to do assignments 8, 9, 10, 11. Okay, so I'm going to unpublish these two because we haven't done acid yet. So let me remove those from the published list. So basically, assignments 8, 9, 10, 11 are the assignments that you have to do. I'm going to make the deadline date on Monday. What date is that? That would be, Monday would be the 6th, all right? So by Monday, they must be completed, all right? And also, I just want to say some of you apparently are expressing anxiety about feedback concerning the assignments that you have done so far. What I'm going to do, and I'm not trying to do this yet, but I'm going to do it tomorrow. I think I have some time to do tomorrow. I'm going to basically scan those completed work, graded, and send it to you guys via email. All right, so look out for that tomorrow. I should be able to do so by tomorrow afternoon. All right, so that we should help you. And of course, if you look at your graded work and if you have any questions you want to ask, if you think I've graded something in error or whatever, you can of course contact me concerning that. All right. And I think that's it for today, unless there are any questions. If you have any questions, you have only 1 minute remaining. So any questions? If there are no questions, that's it for today. So I'll see you guys on Monday. All right. So take care and have a good evening.
Are we still gonna have class on Monday since it's Labor Day?
Oh, right. Thank you. Oh, how could I forget? There'll be no class on Monday, so I won't see you until next week, Wednesday. Right. Labor Day would be Monday, so no class on Monday. Thank you for reminding me. Okay, so I'll see you next week, Wednesday. Take care.